this is Lad from Astrolab Diagnostics, and today I would like to discuss the effect of PCA as a pre-processing step. PCA, or Principal Component Analysis, is a linear dimensionality reduction method, and it is pretty old. In fact, it's ancient in the context of dimensionality reduction. It's been developed in 1901 by Carl Pearson, the same person from Pearson's correlation. And the cool thing about PCA is that it works amazingly well. I know that nowadays people use TSNE and UMAP and so on, but PCA has been here for over 100 years, and you can still use it in many different contexts to reduce dimensions on your data. PCA is often used as a pre-processing step, where you take your raw data, you apply PCA, you take the top n components, and you run your method of choice on these n components. So if your starting data is 50 dimensions, you run PCA, you take the top 10 dimensions, and you run your method of choice. The advantage is that you save memory and you save time. Running algorithms on 10-dimensional data is usually faster and less memory intensive than running them on 50-dimensional data. And here is an example from the documentation for our TSNE and our package that runs the TSNE dimensional reduction algorithm. One of the parameters is PCA, and it lets you choose whether you want to run PCA before applying the TSNE algorithm itself. And in the past few months, I encountered two interesting scenarios when speaking to other researchers. The first one was concern. Why are we throwing away so much of our data before running the algorithm? What if there's something important there in the context of site-off? If you go from 50 dimensions to 20 or 30, you throw away 20 dimensions of data. And in the context of single-cell RNA sequencing, it's very common to start from 20,000 dimensions and go down to 1,000. So there is some concern there. And the second comment I encountered, which I found a bit confusing, is let's just run our method of choice on all of the PCA components. So we take the data, we run PCA, and then we run the algorithm on all of these components. And yeah, so this is the two scenarios I encountered. And one important thing I want to mention is that oftentimes between this step of taking the components and running your method of choice, you calculate pairwise distances or a k-nearest neighbors graph. In fact, this is pretty common to go through that step when analyzing data. So it's not that you go from the PCA components to your method of choice, you calculate distances, and then you go to the method of choice. And this is definitely true for TSNE and many other algorithms. Phenograph and the clustering used by Surratt, which is a variant of Phenograph, also comes to mind. So what we want to talk about is not the raw data. What we need to be concerned about is distances. And PCA is really good at conserving distances. In fact, when you go and use all the components, it is guaranteed to maintain the distances exactly. So what we need to look at, sorry about that, is not the raw data, it's the distances. So as a case study, I took a site-off sample with 55,000 cells and 34 surface markers. And just for the clarification, I'm going to use all the cells for the PCA calculation. Just to show the figures, I'm going to use 200 points, just because distances are like 200 points is 20,000 distances. So using all cells is going to be a whole bunch of points for the figures. And what we care about is this. So this is the distribution of distances in these cells, and we see that a bunch of cells are similar to each other and a bunch of others are different, a bunch of pairs are different, basically what we would expect. And to look how this behaves in the context of PCA, we can use a visualization called the shepherd plot. Or Shepard, I'm sorry, I'm not sure how to pronounce that. And in this figure, the x-axis are the original distances. So every point here is a pair of cells from the original data. The y-axis are the distances in the principal component space, and specifically taking the top 10 components. So we started with 34 dimensions, we ran PCA, we took 10 components, we calculated distances. And you can see that the correlation here is pretty high. And to make this a bit fancier, let's color code based on the density. So this is the high density peak we saw before, this is the low density peak, and let's calculate the Pearson's correlation. This is only appropriate given that Carl Pearson developed both of these methods. And the Pearson's correlation is 0.99. So for, I wouldn't say all intents and purposes, but for many intents and purposes, um, using the distances from the PCA is the same as using the original distances. The correlation is high, and they're about the same. And picking the thickest area in this here, in this correlation over here, let's say the thickness here is about 2. So there is some variation when you go on a distance basis, but all of the cells in the low peak are still in the low peak. All of the cells in the high peak are still in the high peak. So that's one part that you shouldn't be that worried about. Um, but then, of course, how many components should we use? And you can use the Shepard plot to investigate that. So I actually generated the Shepard plots for all the values from 1 to 34. And this is how it looks when we're taking just the top PCA component. So we are comparing distances in the 34th dimensional space to the one-dimensional space of the PCA component. Probably not as fancy, not as consistent as before, but still pretty good with a correlation of 0.84. And now we can increase the number of components we use and examine the Shepard plot and the correlation, and it actually converges pretty quickly. So this is the figure we've seen before with 10 components. The correlation is 0.99, and if we keep going, oops, then we're going to cache. Then you see how it becomes thinner and thinner until when you're using all of the components, the correlation is 1 and we see perfect match. And again, this is because PCA preserves the distances. So, going back to the previous discussion, using all of the PCA distances, all of the PCA components for a distance-bench algorithm is the same as using the original data. And if you're worried about losing data, you can start from all of the components and then go back and decide, okay, this is what I feel comfortable with. Personally, 10, probably fine. I would say that 7 is where I would start worrying, because we start seeing a population of distances that diverges from the main diagonal. So in this case, somewhere between 8 and 10 makes sense. So yeah, so here just some things to think about when looking at PCA as a pre-processing step. And a few take-home messages. If you're fitting distances into your method of choice, the information loss, so to speak, when using a subset of PCA components is negligible. And you can always use the Shepard plot to look for any suspicious trends and decide what you feel comfortable with. And finally, this is applicable to single-cell RNA sequencing as well. This is applicable to any data that you use. You can always go back to Shepard plot and see if it fits within your comfort zone, so to speak. So this was a few minutes about using PCA as a pre-processing step. Once again, I'm Elad from Astrolab Diagnostics, and feel free to reach out if you have any questions.